Hi everybody. Okay, this is my second video. I got an awful lot of emails in the last 24 hours, and to be honest, I don't know if I've got time to go through all of them, but I'm going to try to do it tonight. I appreciate all the emails. I like to try to at least say thank you when you send me an email. If you got questions, of course, I like to answer them, but I do have another life that takes up 99% of my time, so forgive me if I don't get right back to your emails. What we're going to do today is we're going to talk a little bit more about what it takes to more structurally design these aircrafts and the systems, and the things that make up all those different components. But you have two things: they have to be functional and they have to be light. Because an aircraft, the lighter it is, the better they fly. So what I'm going to do here is talk a little bit about how I come up with some of the different. Hang on, I gotta set this on the right thing. Thought I had it. There we go. So if you look at this rib right here, this rib is made out of plywood, and it used to make up the ribs on this door right here. Okay, so on the original door, this is the third door. So if you weigh this, it's about 5 grams. Yeah, 5 grams. And if you look at it structurally, you can bend that wood and it breaks. Pretty easy. So we've got a fracture in 2 places. So you say to yourself, okay, how strong does it have to be? Well, it's got to be rigid enough to keep the door so when the air pressure on the airplane's blasting against it, it doesn't deform and jam. But you also have to keep in mind there's no reason to have strength in this direction on it, okay? Because when that when that rib's in there, the skin here will give you that kind of rigidity. So you then say to yourself, okay, the carbon fiber, I can't break it, okay? But what does this weigh? Almost 2 grams, okay? So it's about a third of the weight and probably 100 times stronger. And if you use it correctly, if you look at this door and it's hard to see, this whole door is fiberglass only with carbon fiber where I need the strength. Okay, the original door weighed about 12 ounces. And this door, if I set it on ounces, this door weighs 7.4 ounces now. So I saved a lot of weight, but it's 100 times stronger. Okay, and if you look at the carbon fiber here, I can't even deform it. So, and it's probably about too strong. So keep in mind when you're building these model airplanes, there's a lot of different forces going on, and you got to just kind of practice. I've never gone into all the math and algebra to figure out what, how these wings really work. I've just built mock-ups. So, if you're going to have a top spar and a bottom spar on a wing, top spar normally is in compression. Bottom spar is normally in tension. It's being pulled. To pull carbon fiber apart, it takes thousands and thousands of pounds, depending on, this strip right here would probably hold 1,000 pounds, okay? But in compression, it doesn't do very good, okay? So the shear webs that go between your ribs is what takes up a lot of the compression forces. On my B-36, I had just balsa wood shear webbing. That's one reason my wing flexed. Now, if I was building a B-52 or a B-47, you want that wing flex. But on a B-36, your ailerons and your flaps would jam up or rub, and that's what my problem on the B-36 wing was. So it's just very important to keep in mind that as you're building all of this, you should do some mock-ups and test them. I've built so many spars and tested them. If you remember some of the old pictures of the B-36, I actually had my son, at the time that weighed 99 pounds, sit on a section of the wing that was all carbon fiber spars, and it had some carbon fiber shear webbing, and it held 99 pounds, and it deflected very little. So if you know how to use carbon fiber, which I'm not saying I'm an expert, I've just learned from trial and error and thrown away a lot of money, how to do that. So, but the nice thing about carbon fiber is it's kind of idiot proof. If you know how to epoxy and put fiberglass together, you can use carbon fiber. This rib, believe it or not, I made from making a sheet that was about 24 inches long, 12 inches wide. And basically what I did is I take a piece of plexiglass, put 5 coats of wax on it, throw some PVA on it, laid out my two 5.7 ounce carbon fiber cloth, use a West System resin to really squeegee in and bathe it all. Squeegee out almost all of the resin once you've got it bathed to make sure there's no air bubbles. And then take another piece of plexiglass that's been waxed and you've put the PVA on it, sandwich it, put 100 pounds on it overnight. The next day, peel them apart, and you end up with a sheet of this stuff. And I cut my ribs out of that, and it is working fantastic. My next project after the C-130 will probably be a very, very large 787. I'm going to build the wing out of foam, balsa, and fiberglass, that only to use it as a plug, because on that airplane it's going to be basically I'm going to pull from the molds fiberglass skins, but all the ribs will be carbon fiber, and the top and bottom spar will be carbon fiber, and all the shear webbing will be carbon fiber. And I think it's going to be an absolutely cool, very large, and very light wing. So, but that's probably a year and a half from getting done, because once the C-130 is done, I'm going to take a year off just to kind of do some designing, because quite honestly, this project was supposed to take a year and a half, and I'm 4 years into it. Now, I do want to talk just for a moment about never giving up. Now, one of the things that you need to always keep in mind is when I first started doing my molds and stuff to do fiberglass parts, it was a disaster. On the B-36, the nacelles, everything, they were sticking in the molds. I could never get the plug out. And there was a German guy who I become really good friends with that started explaining to me some of the mold releasing techniques. And the PVA tin is what I started using. So basically, I would build the nacelle out of foam, put some balsa wood on it, and fiberglass it, get to look exactly the way I want, put my panel lines, put everything in it I want, and then I would take the nacelle and run it through my bandsaw so I have two halves, okay? Then what I would do is lay the fiberglass on, okay? And then, well actually I'd wax it 5 times, put the PVA on it, then I would lay my fiberglass up on it and let it cure overnight. Then I'd pop it loose, and that's how I got my mold. Okay, so now I feel extremely comfortable building the molds and the parts. Now, if you notice, there's no carbon fiber in this because this is just for aesthetic. This is to look like a nacelle. It's not going to be reinforced in any of the internal structure. All of that's done with plywood and carbon fiber. So if you're going to build something extremely just for aesthetic light, like this right here only weighs 1.2 ounces. Okay, there's no reason. I see people always putting carbon fiber in this. Now, if this plane was going to go 150 mile an hour, there's going to be a lot of aerodynamic forces on it. I might have put some carbon fiber in there so it couldn't buckle, but on this, it doesn't matter. You know, the entire nacelle, actually, this was one of my first ones where I had a whole bunch of layers of cloth on it, but this entire nacelle weighs 4.5 ounces. But the nacelle that will fly will weigh 3.8 ounces. So everything's weight on these big airplanes. So with that said, I want to talk about the team you're going to work with. Believe it or not, I've got a team of people that help me. Basically, it's just knowledge base, and I've had a lot of problems with this. Everybody says that I mean, we all know in life that it's teamwork that gets anything done. But you got to be very careful who that team is. Because if you don't pick veterans, one person can pull your team down. On the B-36, I had researched all these different landing gear companies, and one company told me without a doubt, oh, Damon, I've done all these jobs over in England for these big, the Large Model Association planes that weigh 300 pounds, all this stuff, and he really hyped it up, and I thought, okay, I believe him. So basically what he came up with on my nose gear is this bastardized idea. You know, I tried to use it. It was heavy. I mean, this thing by itself here, okay, just this mechanism weighs 3 pounds. 3 pounds for a nose gear that doesn't even have the wheels on it. Okay, 3 pounds. So, and there's no up block on it. So when you pull G's, it would come down. So I spent almost $1,000 on the two main gears and the nose gear from a guy who said he was a pro, and he just didn't want to take the time to meet any of my specifications. He came in 3 times overweight, and most of it was just junk. It didn't work right at all. I mean, it's just junk. The main gear, which I almost injure myself every time I pick it up, this gear right here weighs 10.5 pounds. 10.5 pounds. And this is a carbon fiber tube that I put it myself. And the guy had the audacity to say, I don't know why you're using carbon fiber. The stainless steel was fine. Yeah, you know, I'm trying to be nice right now. But there's, and I don't even have the 2 massive air cylinders on this. So this thing weighed almost 12 pounds when it was done. Okay, so that's putting 24, and then I add the nose gear. Almost, when you really got down to it, it's about 28 pounds to the airplane in just landing gear. And what's really bad is there's no up lock on this. So I had to have 150 PSI to keep the gear up. This is one of the reasons I gave up on the B-36 was I had wing flexing. This landing gear was a disaster. The plane was going to weigh too much. And then I had a guy that was building a new bar that wanted to buy the airframe to hang on the ceiling, and I needed the money. The B-36 will get built one day. It's just not on high priority because of all the disasters I had. So I guess what I'm trying to say is when you think about the people you're going to work with, like I met a guy through Ceph a couple of years ago or 6 years ago named Berger, and we've become really, really good friends. Berger is a genius when it comes to small microcontrollers. Now, on the internet, I had a young kid who thought and he's a smart kid, nothing against him, but he reached out and said, Mr. Atwood, I can build you the sequencers for your main landing gears for your C-130. I said, okay. And what he did was kind of came up with something that looked like the old Heath kit. And it would have been big, bulky, a lot of wires, a lot of soldering. And the kid's smart. He just didn't have the experience yet. He didn't have the skills yet. Berger saw this. He reached out and said, hey, I can make you a little microcontroller. And if you remember from my other videos, it's about the size of a postage stamp, does everything. I'm not sure how Berger, with his fat fingers, got in there and soldered everything. But he's part of that team of what I call geniuses. Okay? So be really careful when you're reaching out to people to help you, because many people will tell you, oh, no, you can't do it that way. You're doing it wrong. Look, I don't know how to say this properly, but I have learned so much on my own how to do it better for myself than what most people tell me to do it, that I don't know what they're talking about. I don't know if they have the experience of doing it. You know, my big MSL, that, you know, it's been around for almost 9 years flying. I had people call me out and said, there's no way at, 60 watts per pound it's going to fly. And, you know, I did all the math, and there's no reason it wouldn't fly. The wing loading was right. It sure was going to have some drag, but it was going to fly. No, you can't. You got to have 150 watts, a pound. And, you know, that's aerobatic. You know, even good scale stuff at 100 watts a pound flies wonderful. But believe it or not, the MSL is between 60 and 75 watts a pound, and it's flown for 9 years. So be really careful who you listen to out there. Go to the people that have success, and you can see by the airplanes they're flying they have success. Okay, many people, when you start to do cool things, are going to come to you and say, oh, I can help. And they really can't. I mean, it's nothing against them, but you got to pick the team of veterans. Okay, because if you have a team of some people that are trying to help that don't have the skill, you're going to throw away opportunity, you're going to throw away money, and you're going to throw away probably the fact your airplane's even going to ever fly. So with all that said, what I want to do now is move back into the software, and hopefully up here in the corner of your screen, you're going to see some of the 3D software I've been talking about. And I'm going to go to the Mosquito real quick, because I had a couple of emails with people asking me about the way that the Mosquito worked. And what I want to do here is show that when I designed the Mosquito, there was a couple of things that really had me worried, and one was doing a somewhat scale landing gear. And if you look here, you can see that, I got all the geometry to work right. Now, right now, this green cylinder here I have drawn as an air cylinder. But I don't know if the air cylinder is going to be strong enough, because if you really look at the geometry going on here, when it gets up to about here, it's really pulling hard on these struts to suck that wheel up in there. And that wheel's probably going to weigh a pound. So this may be a jack screw. Since I had such great success with a jack screw on the C-130, I might make that, out of the jack screw. But if you notice here, by bringing all of my CAD drawings into it, I've actually virtually built the airplane, so I know all the parts are going to fit. All of this came from CAD drawings, and I basically built the airplane in 3D, just like I would build the real one. And I would see what steps I had to do to get what parts to go in. If you can see, here's my big Hacker motor, my ESC, my 2 LiPo batteries, because I'm going to have 12S on this. I even went to the point of animating the Bombay doors, just to see how they're going to swing and how their hinges are going to work. The Bombay door hinges, believe it or not, whoops, is really a mess on this airplane to get them to swing out so that you have a tight. See, if you look at the hinges here, hang on a minute. Okay, those hinges are to get it to swing out and open so that there's nothing touching the outside skin or the skin of the Bombay doors. So I don't know if this will be electronically activated or air activated. Probably air, because I might be able to keep it light. However, if I go to electric main gears, I may make this electric, because air systems are heavy. People don't realize the air tanks and all the plumbing and all that crap gets heavy. So that is one of the pictures I wanted to show on the Mosquito. The other Mosquito picture I want to show is the wing. And on the wing, let's see, I wanted to show you how I designed it. So it comes off the wing tubes, okay? But I want to show you how I've designed the, let's see if I can get in here and get a good perspective in here. Let's see if I can remove this top skin. Probably going to, yep, I hid the whole thing. So let's render this, and you can probably see it better like that. Okay, so if you look, hang on, let me render that higher resolution. Okay, you can see the top spar, bottom spar, and this shear webbing. The shear webbing is what's going to create most of the strength in the wing. If you have the spars made out of carbon fiber and balsa, in tension they're going to be strong, but in compression they're not nearly as strong as you would think. But by having the shear web laminate everything together, you will end up with almost like a box truss, and it will be really, really strong. So, and one reason I have these sub ribs in the wing, sub spars in the wing, is because I like really, really thin wing skin, because that's how you can build light. A lot of people will put really thick skin on their wings, and they don't have any idea how much weight they're adding. Let's see, I want to show, okay, I'm also working on a A7 project, which is about, I don't know. Right now I plan on building a 787 next, and then the Mozzie, and then an A7. And then one day the B-36 again. But like, this is the nose gear of the A7. The thing that I love about 3D is that I was able to get into the kinetics and really understand how all the different parts are going to work for the nose gear. So if I... then one thing you can't see here is right about here, there's going to be an up lock that will swing into, and when it clicks into it, it will be locked. Basically, it'll come up and hit a spring, but when the servo is in the down position, it will open and let it down. So that way, I have a mechanical up lock, and I have a mechanical down lock right here. So that's the nose gear for the A7. And we will render this. And you can see what it all looks like. And there's the oleo strut, like on the Royal A7. Okay, the other thing I want to show you on the A7 was the, let's see. Okay, the airframe is going to be kind of a pain. Whoops. Thought I was opening the A7. A7 Corsair. Oh, this is the main landing gear on the A7. So that shows how the main gear will retract on the A7. Okay. And where is my A7 fuse? Okay, so basically here you see the fuse I've been designing on the A7. Now, the problem is the size of the ducted fans that are available weren't big enough when I started this, so I'm going to have 2 ducted fans in this. And a lot of people said, oh, that's crazy, it's not going to work. So far, all of my testing shows it's going to work. So let me, hang on a minute, let me remove a couple of the ribs here. Get you in here to see how this is going to work. Okay, so basically you see the 2 ducted fans. I have a common air duct that comes in that's going to feed the 2 ducted fans, and then I have them come back into 1 duct for the exhaust. The mold and everything for building this is going to be an absolute pain in the butt, but I know I can build this bastard. It's just going to take a lot of time. This is not for a couple of years down the road, okay? If I'm live 10 years from now, these will all be done if I don't have a heart attack between now and then. So the last thing in 3D I wanted to show was, that's all of it. Okay, so let me get out of 3ds Max. And what I want to do now is I had a bunch of emails about airfoil design. And I'll show you it's not hard at all with this program. So basically I go into the 5-digit. I pick basically, oh, hang on a minute. I think I stay with 0. No, thickness. And yep, here we go. So basically you can see, there we go. So basically here you can see that I just came up with a simple airfoil. One thing to keep in mind that people don't understand, okay? And I'm not saying I'm an expert at this at all, okay, but I've figured it out. If you look at the scare airfoil on a lot of jumbo jets, and let's pick like a 727, at the root, that airfoil is almost inverted. And it's got to do with the way the airfoil is designed to fly at 35,000 feet and be efficient for lift and fuel consumption. When a 727 gets slow, it has to have the leading edge devices. It has to have its flaps. It has to have everything to basically make it a massive undercambered wing so it can land. So on model airplanes, if we were to build a quarter scale 727, it's not going to weigh 25% of a real 727. It'd never fly. Well, it might if it goes 500 miles an hour. But, and sorry, my dog's down here playing with a toy, so I'm going to have to take the toy away in a minute. So the thing is that when we're building our airplanes, we have to build an airfoil that's going to be conducive to flying the scale speeds we want to fly. C-130 had somewhat of an airfoil like this because it's not designed to go real fast. It's designed to lift a lot and carry a lot. Okay, so just keep in mind when you're looking at airfoil designs, you can go on the internet and find all the NACA airfoils for the Boeing aircraft, the Lockheed, and all of those. If it's something that's designed to be very fuel efficient and go fast, you may not want that airfoil. If it's something designed to lift a lot, like a C5 or a C-130, the airfoil might work fine. So you just want to research that. And so that's what I wanted to talk about here. Real briefly on the AutoCAD part of it, I want to really briefly just talk about getting in here and thinking structurally for a minute. So let's just say that you're looking at the elevation of a wing, and this top spar is going to be in compression because the wing's lifting up. Bottom spar is going to be in tension. It's the shear webbing, the way you connect these two, just like a train trestle. When you look at a train trestle, you see all the girders between the top and bottom ones. That's where all the strength in the bridge comes from. It's not in that top or in the bottom. It's everything in between it. If you look at an I-beam and cut out the middle web of an I-beam, that top would just be as flimsy as can be and wouldn't hold anything. It's that vertical component. So the shear web in the wing is what creates 80%, if not 90% of your strength. And a lot of people really don't take into account how they're going to build that shear web. The greatest shear web in the world that you could build would probably be the thinnest and strongest material. So let's say it's a 32nd piece of balsa wood and both sides is laminated with carbon fiber. You'd have to weigh it to find out if there was a weight penalty in that. But if that's a shear web and you have a carbon fiber top spar laminated and a carbon fiber bottom spar, so it's carbon fiber to carbon fiber epoxy together, on my 787, that's the way my spar is going to be made, and it's going to be extremely strong. Now, when I go through all that testing and mock-ups, I'll of course video it and show all the testing, but it's going to be crazy strong. The last thing I want to show, and I thought I had it open, I must have accidentally closed it, is talking about the cubed wing loading. And cube wing loading. And I always go to this one, hang on a minute, it's taking a while, here we go. So if you look at this cubed wing load calculator, it kind of tells you everything you're going to need. Now, I'm not going to go into Reynolds numbers, I'm not going to go into all of the weird math that goes into designing a wing. There's enough calculators out there that you can build a wing and you'll know how it's going to perform. So let's just, for sake of argument, let's say I have a 500 square inch wing and the plane's going to weigh 100 ounces. Now, that's 15.5 cubed wing load number. If you look down here, that says that's a racer. Now, one thing I want to really make really clear to a lot of people out there, there are very experienced pilots that are flying big Zeroli birds that are way overweight. They're lead sleds. But because planes are bigger, you tend to fly them faster in the sky because of the perspective. So a lot of times you're going much faster than you really think you're going. The C-130, I'm actually going to put an Eagle Tree system telemetry just for airspeed, so I have a stall indicator. Now, it's not going to go by the angle of attack. It's going to go by a given airspeed. But if I'm within 5 miles an hour of what I believe the configuration of landing should be, I'll get a little bitty beep telling me that, okay, I'm getting slow. However, there's a lot of airplanes out there with 17 wing cube loading, and they're flying fine. But the heavier the airplane, the less that gap is for you to make a mistake. If you get behind the airplane, you get low and slow, and you're going to get bit very quick with a high wing load. Okay, but let's just say for sake of argument, and I'm not going to go into the square and all that stuff, but let's just say we go up, we double everything here. We go to 1,000 square inches of wing, but we go to 200 ounces of weight. If you look, that wing loading just went down to 10.9. Let's go up to 2,000 square inches, and let's go up to 400 ounces. Wing loading is down there of a trainer now. Now, on my, you know what we should do real quick is be patient with me for a minute. I want to show you how I'm going to measure the square inches of my hang on a minute. Get my reading glasses back on. So what I want to do is look at surface areas. So what I'm going to do is I'm going to measure the surface area of my C-130, okay? And I'm going to go into Tools, I'm going to hit Inquiry, and I'm going to go to Area. And basically, I'm just going to do this really quick. Now, I'm not taking out, nacelles. Any place there's a nacelle, you do lose a little bit of efficiency of the wing wherever the nacelle is. I'm not going to take that into account right now. And I'm not even going to include my wing tips right now. But if I look at this airplane, I end up with 2,549 square inches right now. Okay, now, sure, I'm supposed to take out the root of the wing. So let's say I'm at 2,300. So let's go back to this, and I'm going to put in 2,300. And I know I'm going to weigh around 1,000, about 62 pounds probably. So I'm going to put in 1,000 ounces. Okay, I'm going to hit it, and it says I'm at 15.7. That is high. Okay, that's one reason I'm trying to get the weight out. But let's say I just get it down to 900 ounces. Okay, I get 100 ounces out of the plane. And boom, I'm down to 14. Okay, so anything you can do in the airplane to save weight. And, let's say the airplane weighs 62 pounds, 16. That's 992. So if I'm at 992, I will be at 15.5. That's considered a racer, okay? But this is a 160-inch high aspect wing. It's a big old wing. And I know that there are some calculators that take into the aspect ratio of the wing that I've used that give me a little bit better wing loading calculations. But there's so many calculators, there's so many people out there that you can turn to that can help you with all this. So I hope this helps you all. If you have any questions at all, please, of course, reach out to me. I'm going to put my Gmail account now on my videos so people know how to get out, reach me, and my Facebook. And I hope this helps everybody. I really do. I love doing this. I don't have a lot of time to make these videos, but I really do, and I really do enjoy doing this. So whatever you need, let me know, and I hope everybody has a fantastic day. And I'll be making more videos like this very soon. Thanks, everybody. Have a great day.